Okay, welcome back. We're now going to be talking about, well, first some laws about polynomials, when polynomials are represented as lists of coefficients, and then move on to define division. And when we come to division, it's a little bit like when we come to division in natural numbers or integers. We can't really solve equations using division with natural numbers. We have to move to the rational numbers. And similarly here, polynomials don't always work out nicely to divide. We may get a remainder. But if we move on to let the polynomials not be finite coefficient lists, but infinite coefficient lists, then we can actually define division unless we divide by 0. So towards defining division, we first look at a little bit of the properties of multiplication, and that's because division is specified using multiplication. Okay, first some types. So I'm assuming here that we have addition, which is type, well, basically, oh, now I managed to click something bad. List of A to list of A to list of A, where A is a ring. So normally it will be real numbers, but actually more generally the type A could be something else. Multiplication, which I will write with mul here, just to be extra clear, it will also have the same type. And I will have one other asymmetric operator, and that's scaling. So let's use scale, and that takes an A to a list A to a list A. And scaling, that's what you might imagine. If I scale by 2, all the coefficients should become twice as big. Okay, addition, multiplication, and scaling. I will actually also use map. So remember the function map, which given a function from A to B, will give you back a function from list of A to list of B, where you apply the same function to all elements. Okay, so now some things we want to use later. So if we multiply a singleton list, so just a constant C, by any list of coefficients, then we would like this to be the same as scaling. So if this polynomial, I mean, that's always a constant C, so multiplying that with the coefficients here should be the same as scaling all the coefficients. So this should be equal to scale, oops, that was a bit hard to read, scale C BS. And that in turn, scaling, can be written using map. So map C times BS, where then this multiplication operator comes from the ring. Okay, so that is multiplication with a singleton list. Let's also see what happens if we want to multiply by a other special list, the list 0, 1. Well, remember, what is 0, 1? That's actually a representation of x, or the identity function. So the constant coefficient is 0, the coefficients in front of x to the power of 1 is 1. So this is multiplying the BS, represented polynomial, by x. So let's just make a very simple example down here to get a feeling. So we're saying basically we multiply by x, say 1 plus x plus 2x squared. Well, clearly that is x plus x squared plus 2x to the power of 3. And the list representations here, this is the list 0, 1. This is the list 1, 1, 2. And this is the list, well, it continues with 1, 1, 2, but it starts with a 0. And actually, the notation, the operator for list cons, so in extending a list one element, this is actually equal to 0 followed by the list 1, 1, 2. And this is a general rule. So if we multiply by x, that's the same as putting a 0 in front. So you see the coefficients here are completely unchanged, just shifted up one step. So mul 0, 1 bs, that's actually 0 followed by bs. So we don't even have to look at bs, we can just shift it away one to the right. And then it's also worth noting a law for addition. So if we have a list A, AS, remember lists here represent polynomials. So this is the same as the one element list of just A plus 0 followed by AS. You can put parentheses in to be extra clear. So notice here I've said we use plus on lists. So this is a list representing the constant polynomial returning A, and this is the list representing the polynomial which starts with 0 and then continues with AS, which also, given what we talked about down here, or the law here, is the same as x times AS. So AS shifted up one step. And shifted up one step, I mean, that's what me being in the second position of the cons constructor means. So here we have basically a list starting with A and having 0 at the as the rest, and here we have the list starting with 0 having AS as the rest. Okay, now we have some properties that we can use later on. Let's move towards division. So the question of division, in general, we want to be able to divide some polynomial x by some other polynomial y. But as we can define this as x times 1 over y, that means we only have to define recip, which is the function that computes 1 over. I mean, defined. So recip of x is 1 over x. So instead of defining the 2-argument division operator, we define just the 1-argument recip. And then that's hopefully a little bit easier to implement. And how is this specified? Well, recip is specified that we're looking for a bs such that if we multiply as by this bs, we get 1. Where 1 here is the polynomial 1 followed by 0, or by the empty list, the singleton list 1. Okay, so the whole specification of the recip function is recip as equals bs should be the same as multiplying as by bs is 1. So if you see, I can substitute recip as here. So this basically means mul as 1 over bs. Oh, sorry, 1 over as. Which then should be 1. Okay, so I'm specifying it as a solution to this equation, and I will use that when trying to go through towards finding a definition. Okay, so I will now focus on the case where both lists are non-empty. And why is that? Well, at least if we want to divide, if we want to compute the reciprocal of an empty list, that would be the same as computing 1 over 0. and 1 over 0 doesn't have a solution. And why can we see that? Well, if we would set the AS list here as 0, then we're trying to solve the equation, which I will write in red because it doesn't work. We try to solve the equation mul empty list BS equals 1. But we know that mul empty list BS for every BS is the empty list, is 0. And 0 is not equal to 1. So there is no solution. So actually when we ask ourselves up here, does there exist a BS such this holds? Well, that will only be possible if the list AS is not 0. And one way of ensuring that is to say it doesn't have any leading zeros and it should be at least one element long. Okay, so we collected that up at the top here, saying the recip of the empty list is error division by 0, and the rest is then the question of recip for a non-empty list. Okay, so we know the specification. I've extended it slightly here. It now says 1 followed by 0, but it's the same intention as before. And I want to start by computing a simple case, which is just 1 over 1 minus x. So where 1 minus x is represented here by the list 1 minus 1. So A is 1 and the AS part here is a singleton list minus 1. Okay, let's try to get a feeling for what laws on the mathematical side should hold, where we can rely on here. So let's compute what eval of this multiplication is. So what is eval of mul of this list, which is 1 cons minus 1? What is this multiplication with b? Oh, sorry, it should be b. Oh, there's space enough. B cons bs. What's this evaluated at x? Well, we know that eval should be homomorphism from this multiplication to multiplication on the function level. So we can take that 2 steps down and say this should be the same as evaluating, evaluating 1 cons list minus 1 on x times evaluating bs on x. Okay, once again, I've matched bs having 2 elements, so it should be b cons bs on x. And just to avoid me cluttering this up too much, I'll just write a single dot as the multiplication sign. Okay, now let's see, what is eval of 1 minus 1x? Well, we can turn the crank of the definition of eval and we'll find out that this is in turn equal to, well, 1 is the constant, so 1, and then minus 1 is the x term. So 1 minus x times the evaluation of the other one. So here I will actually go towards the sort of mathematical definition here. So I will write, first give a name, I will just call it q, and then I say where q equals the sum from I equals 0 to infinity of bi x to the power of I, where b0 is this b and b1 and upwards are in the bs list. Okay, and clearly 1 minus x times q, that is equal to q minus x times q. I just multiplied q in. Well, what do we know now? Well, we can identify coefficients. So you can see that when we multiply by x here, all the exponents will be raised one step, but we still want this whole thing to be equal to the right-hand side. Oops. This right-hand side. So this whole thing should actually also be equal to 1. So this is the equation we need to solve. Let's make it green. So we're looking for coefficients b1, b0, b1 and so on to satisfy this equation, where q is equal to this infinite sum. Now it's useful to draw this a little bit graphically. So I will actually move one slide forward where I've already written out that graphically. The previous calculation is the same. So here I've written the infinite sum one term at a time, and then some dot dot dot. So first we got b0, b1x, b2 x squared, b3 x3 and so on. And then we should subtract x times q, which means x times, so subtract x times b0. And I've moved this one step. Remember, I also said that multiplying by x is shifting the coefficients one step. So now we have b0 below b1 here. Similarly, b1 is below b2, b2 is below b3, and so on. So this is the first row here is q, and the second row here is minus x times q. And this should evaluate to, as we said, 1, and 1 is equal to a constant plus 0x, 0x squared, 0x3, and so on. And now we can identify the coefficients. So we know that as this should hold for every x, we'll be able to say that this is true only if all of these equations are solved. So the first equation, I mean, it's not very nice to have an infinite number of equations, but it's nice that they are very simple. I mean, the first one is actually in solved form already. The first one says b0 is 1. The second one says plus b1 minus b0 should be 0. Well, b1 minus b0 is 0. That's also rather easy to solve, especially since we know that b0 is 1. Just means that b1 is also 1. And if we look at the pattern here, we're going to have exactly the same shape of all of these. It's always bi plus 1 minus bi equals 0, meaning that bi plus 1 should be equal to bi, which is equal to bi minus 1, and so on, all the way down to b0, which is 1. So even though it's an infinite equation system, we can still deduce that all of the b's should be 1. So by translating this to the sort of mathematical world and then checking, knowing that we have to match the coefficients, then we can conclude that all the coefficients should be unity. Okay, what have we now proven? Well, we said we computed the reciprocal of 1 minus 1. And we got the infinite list, or the stream, of just ones. So as it's infinite, it's not a polynomial, but it is what is called a formal power series. And if we write it on the mathematical side after applying eval, we can say that 1 over 1 minus x, which is what we're trying to represent here, is the infinite sum of bi to x to the power of I. And as all the bi are 1, this is just 1 times, which is this sum, which you may recognize from some other maths course, that 1 over 1 minus x can actually be written as the infinite sum of x to the power of I. So, I mean, if you want to be even more explicit, it's 1 plus x squared plus x3 plus and so on ad infinitum. So now we should be a little bit worried about convergence of these sums. That's why it's called here formal power series. So a formal power series is actually just this infinite list of coefficients. It doesn't talk about its convergence, and it's not at all clear for which x this sum would converge in general for an arbitrary list. So it will always work for x equals 0, because as you can see, this sum, if x is 0, then this will evaluate, so all the x terms will be 0, so it's only the constant term which survives. So it's always defined at 0, but how far away from 0 we can get, that depends. And in this case, if we start from 0 here, it's clear that we can move towards 1, but not to equal 1, because if we would insert 1 on this left-hand side, it will be an undefined expression, 1 over 0. And if we check what happens on the right side, if we try to compute it for x equals 1, it would just be an infinite number of 1s. So for any x less than 1, it should work. Or actually, the radius of convergence here. So the radius of convergence is 1. And what it means is that actually the absolute value of x has to be strictly less than 1 for this to converge. Or at least for this equality to hold. So strictly speaking, it's not necessarily for the list to converge, but for the equality to hold. So let's see what happens if we go out of this. Well, if we go out of this range, all bets are off. As you saw in this particular case, where this wasn't defined, where x was equal to 1, this is infinity, or tends to infinity, and this is, well, I guess you could say it's infinite. But if you put x equal to 2, so what happens if we do 1 over 1 minus 2? Well, that's just 1 over minus 1, which is minus 1. So notice that it can very well be the case that the left-hand side can be defined for a radius of convergence. I mean, every x which is not 1 works there. But the right-hand side, this infinite sum, has this radius of convergence. So you should be careful when evaluating these things to not do it too far away from 0. Even though for the formal power series, we can add them, multiply them, subtract them, even compute derivatives and so on without caring about that. But when we want to evaluate them in the end, we have to check the convergence radius. Okay, let's now move to the general case. So we had this specification for recip, and we computed it so far only for the case of 1 over 1 minus x. But if we don't know what AAS is, it's just anything, then let's look at what multiplication does for a non-empty list times a non-empty list. And this is one of the exercises. If you have two non-empty lists, the first term of the result is the constant terms multiplied. And if you think about this as basically polynomials or infinite power series, it's clear that the 0th order component is just these two multiplied. And then when you get up one level, then you can either scale the whole BS list by A, or, well, I mean, added to multiplication of the whole tail here with the whole B cons BS. Okay, and now we have the equality saying this will be 1, where 1 is actually also equal to a 1 in the 0 component, and then 0 for the rest of the polynomial, so the empty list. Okay, and now we can try to compute to see how can we solve this equation, because remember, this is a specification we have here, and what we really want is to find out which B and BS match the A and AS, which are the inputs. Okay, so the first part here in the middle is what I just repeated from the previous slide. And what we need to solve, because lists, even infinite lists, match only if all the components match. So A times B should be equal to 1. That's the first green part. And then this other part should be equal to 0. So scale ABS plus the multiplication of AS and B cons BS should be 0. Well, I can then subtract mul as b cons bs on the right and to move it to the right. So then we said the scaling with a of bs should be minus the multiplication here. Okay, so I've just taken the list equation and made two equations for the head and the tail. Next step is say, okay, this one I can definitely solve. B should be 1 over a. Well, I can solve it if a is not 0. So that is another requirement. So if a is not 0, then we know what the first component is. What about what we can do in this side? So on this side, I have multiplied by b on both the left and the right. So why have I done that? Well, notice that I said here b is equal to 1 over a. So multiplying by b and multiplying by a should be the same as multiplying by 1. So these two scales should disappear. So I'm trying here to get rid of the scaling to just get bs, because remember, the task is to compute b and bs. Okay, so I scale by b on both sides, and notice there was a minus here, so it becomes the same as scaling by minus b then. So the minus sign has moved in there. Okay, so here I've done nothing else than scaling the left-hand side and scaling the right-hand side of the equation. Well, okay, nothing more. I also moved the minus sign in one step, because the mul as b cons bs is unchanged. Okay, well, now I just took the first part here and transformed. I said, well, scaling twice should be scaling with the multiplication. That's one of the laws for scaling, and you can also get it from this definition in terms of map. Now we know that b times a is 1, so that's scale with 1. And scaling by multiplying each component with 1, that's just nothing more than bs. And then I don't have to copy this one down. I can just say that these two should be equal, which are indicated here with a little blue. But maybe I should actually make an equality sign here as well. Erasing. So if I define bs to be the expression scale minus b mul as b cons bs, then the equation is solved. So notice what I did. I split up the equation into the head part and the tail part. I reformulated the tail part in terms of a simple operation on bs. Bs is what I'm after. And then I sort of inverted this operation by scaling by b, where I had scaled by a, doing the same on the other side. And then I just noticed, okay, now I have actually a defining equation for bs. So if we move that into a definition as code, we say that recip of a cons as is b cons bs, where b is 1 over a, and bs is, well, here I've been more explicit saying the negative, the minus sign, the unary minus is actually called negate in our type class implementation. So scaling by minus b, which is minus 1 over a, the result of multiplying as with b cons bs. Now you may get a little sort of unstable here, unstable feeling, because you notice the b and the bs are defined here. So we have a recursive definition of bs. Bs is some scaling of a multiplication of bs. So it's not obvious from this definition, just looking at it quickly, if this will actually terminate. I mean, what happens if you try to compute the first value? But notice that the good thing is that the result of recip starts with b, and b is directly computed from only the first component here. And then the rest, if we want to have one more, so we want the tail of the result, well, to do that, we use the whole list. So the first part we already know, and then the tail. And multiplying it will not move, so to speak, will not move this thing backwards or closer to the head. So it actually is safe computation-wise. It may not be very efficient, but it will sort of recursively build up actually an infinite list BS. And the special case, which is worth testing, if you now specialize B to 1 and BS to the singleton list -1, no, sorry, A to 1 and AS to the singleton list -1, you will see that what comes out is B equals 1 and BS equals the infinite list of ones. Okay, so this is ended up in showing how we can define recip, which is then in turn used to define usual binary division of polynomials, as long as it's not division by 0. And the definition, even though it's recursive, is actually productive and produces the infinite lists as we move along. That was all for this part.